So again, good morning. This is everything that we learned the hard way, implementing ActiveRecord encryption. Thank you so much, Miriam, for the introduction. My name is Kylie Stradley. You may recognize me from a presentation I gave earlier this year at RailsConf in Atlanta, Georgia with my coworker, Matt. This was called ActiveRecord Encryption, Stop Hackers from Reading Your Data. And it was kind of about, sort of just convincing people the value of using ActiveRecord encryption, and we spoke a little bit about some of the changes that we made. If you are jet-lagged, like I am, or aren't sure which talk you are in, we can just do a quick refresh of ActiveRecord encryption so you can be certain you want to be here for the next 30 minutes. It's this really lovely API that we get for free from Rails, right? It provides automatic encryption of database records and plaintext access when you need it. We upgraded our previously encrypted columns with an internal strategy that the team wrote in about 2020, and upgraded some plaintext columns to ActiveRecord encryption. So before, we had this bespoke internal strategy, which was a very easy to use API. If you look at it, it looks very similar to ActiveRecord encryption, right? But we had a couple of problems. The main one, from my perspective, was this key generation bottleneck. To start encrypting records, you needed an encryption key. We found that product engineers were not comfortable generating their own encryption keys, so it was on my team to generate the keys for the product engineers, and it just kind of took a while to get things going. Also, once ActiveRecord encryption was introduced, we were now in the position of maintaining divergent column encryption code. So this was a little harder to do, and you saw the ActiveRecord encryption API I showed you just a second ago. It was a bit easier to do, and keys are actually derived basically at the time of writing code, or you could even consider at runtime if you really want to get down to it. So ActiveRecord encryption was very tempting to our product engineers, and if they started using it without us going through and securing everything, including it relied on this encrypted Rails secrets.yaml file, which is not somewhere that we can actually store our encryption keys. That's like a violation of our service level objective. It could be a big mess. So after we upgraded, we still had a really easy to use API, right? The lovely API I showed you before. We reduced some of our bespoke code that we had to maintain. And now we have a couple of benefits that we just couldn't provide before. Keys are derived at the time of running code or writing code, or I said, if you like to get really picky about it, at runtime, really. We have a strategy now to easily upgrade columns from plain text to encrypted. This could be done with our previous system, but it was difficult and frankly intimidating, so people didn't choose it. And finally, we centralized key rotation. So we took the responsibility of rotating encryption keys from product teams and put it back on our team, a security team. And this made them much more comfortable and happier. So in the previous presentation I mentioned, we wanted to show how straightforward and easy column encryption can be. But we weren't entirely honest, right? Deploying the new column encryption strategy wasn't always straightforward and easy. So this talk is more of a real-world case study. And it's anyone who might be converting from an existing column encryption strategy. So this might be some of you. Those who are working in distributed systems, given that Rails is 20 years old, I expect that this will be possibly some more of you. And those who will rotate their encryption keys. This should be all of you. We can choose to rotate our encryption keys on a maintenance cadence as scheduled, but actually a fun thing about working in security or working at a company that has desirable data is you may not always get to choose when you rotate your encryption keys, right? There may come a time when you just need to rotate your encryption keys and you need to have extreme confidence that you can do it really well and you can do it perfectly, because encryption must be perfect. There's no other way around it, really. So we learned a lot about deploying and maintaining resilient security software. We made a lot of assumptions about what we thought we knew about encryption and what we thought our hardest problems would be. And not to brag, but we did do this with no downtime. We learned it the hard way, but I'm hoping that with this presentation, you don't have to. So we challenged and disproved our own assumptions about what we thought the hardest part of this project would be. And these are some of the assumptions, right? The hardest part of encryption is key management. Maybe this is something that you've read. I learned this in school. One byte in, one byte out, which is kind of a sound bite for a larger problem we interacted with. And then the price of it just works is performance. This is what we believed. So let's get right into it. The hardest part of encryption is key management. So what we thought this meant was things like FIPS compliance, right? FIPS is this standard that you have to adhere to if you work with US government entities. At GitHub, we're not required to work with this standard, but we try to meet it as closely as possible. And we weren't worried about this because we were meeting it using AES. AES considered the best in class for symmetric encryption. We were worried about nonce reuse. Nonce in cryptography means number used once, right? We were concerned about nonce reuse because of the sheer number of encryptions we do every single year at GitHub. And we had this information because we had a previous column encryption strategy in place. The more encryption operations that you do, the more likely you are to generate a duplicate nonce. This is called nonce exhaustion. So encrypting two things with the same nonce is just absolutely fatal to the confidentiality and integrity of AES. So it's very, very important that you do not generate a duplicate nonce and then use it to encrypt two values. But we weren't worried about this, right? We thought we were being very clever. We added the current year as anti-nonce exhaustion data, which effectively derived a new key for each column every single year. Another thing that we were concerned about that you might read about is secure key storage, right? And we weren't worried about this, though, because we were using HashiCorp Vault to store our keys, and we had been using that in part of our previous column encryption strategy transition for some time. So that's everything we thought we knew, right? You go into a project thinking, oh, we know what's going to go wrong. We're not worried. We're smart people. Key deployment is actually an extremely difficult part of encryption. Let's say you have one Rails server, right? And you have ActiveRecord encryption enabled, and you encrypt records with your key, and you save them to the database. And now let's say you add a key as part of your key rotation process. So going forward, all your records will now be encrypted with your new TL key. When you rotate your key, before you've re-encrypted every single record to use your new key, your latest key, this TL key, cannot decrypt purple records, right? Some of you might be thinking, but this will not happen, right? ActiveRecord encryption considers this. And you would be right in this specific scenario. Rails will just move right along to the next key in the list, and you'll be able to decrypt the record. This is wonderful for you. Truly, I love this for you. The Rails guide will take you far in life. You probably don't need the rest of the presentation. But maybe you, like me, work with more than one Rails server, or maybe if today you work with one Rails server, you'd like to work with more. So let's say your app is a bit bigger than just one Rails server, right? Maybe your app is more in the range of like a fleet of Rails servers. And maybe you serve like thousands of requests per second, and you're doing quite a few encryptions and decryptions every year. Here's a really simplified version of the scenario described. We have a couple of servers that are writing encrypted records to the database. Very nice. Now, when you rotate your key, you have to propagate the change to all of your servers. It is difficult to coordinate such a propagation all at once. Can you atomically deploy a key to all of your servers at the same time? I cannot. What does this mean for you, right? Until you've propagated your keys to all of your servers, any processes that may be holding on to references to old keys or any servers that haven't received the new keys yet, you might find yourself in a situation where a record is encrypted on one server. So see, we have this new TL key coming out. It's encrypted with this TL key, but it cannot be decrypted on another server because that server has not yet received the decryption key. So what we learned is just appending a new key didn't work in our distributed system. In a distributed system, to rotate keys, we also had to distribute keys. So before we started this project, our previous encryption service was actually networked, which is maybe not a choice you would want to make. We decided local encryption would be sufficient. But we distributed keys through a database-backed API in that situation. So we didn't have to worry about this type of key rotation and distribution until now. We needed a solution that ensured encryption would happen with new keys only once they were propagated to all servers. So we decided to distribute our key by using a two-key strategy. First, distributing the new decryption key, then distributing the same value as an encryption key. So we can distribute the decryption key, wait for the process to signal that that key has been propagated to all of our servers, and can ensure that it's present on all servers. If we attempt to decrypt with the new decryption key, Rails will do what it does well, and it will just move along in the list and attempt to use the next key, which should be the correct key in this situation, in this system that we've set up, and this works. Once we know that the process is complete to distribute the decryption key, now we can distribute the encryption key. With both keys in place, we ran our specialized migration to re-encrypt all of the records in place with, again, no downtime and no using a plain text mode. So using two keys enabled us to maintain our encryption SLO. We didn't want to use plain text mode. It's very handy, but for us, we had records that were previously encrypted, and we couldn't allow them to be stored in plain text. Also, because we have so many records, our re-encryption process was fairly lengthy, right? So maybe if you have just a couple records, your re-encryption process will not take so long, and it's okay, but it would not be acceptable for that length of time for our records to be available in plain text. So what can you learn from our experience? Well, we learned this during a planned test of our key rotation strategy. And this is certainly one way that you can find out about faults in your system. I do not think that this is the best way to find out about potential faults in your system or your deployment strategy. Your best bet for detecting this type of potential failure is knowledge of your system. So I would encourage you to do some research and understand your capabilities for updating keys for your production servers. Can you orchestrate updating all of your keys at once? If not, how can you roll out your keys to prevent this potential decryption failure? We have a centralized key management system that we push out updates. Do you update keys via push or a pull? What triggers a push? If you use a pull system, how do you trigger a pull? Do you pull for updates? How frequently do you pull? How and when is your data migrated? Is your database sharded? Will data ever move between shards? How will you re-encrypt records for key rotation? How long does re-encryption take? These are the kinds of things that you should think about when you're thinking about deploying your key rotation system. So key rotation and re-encryption of all records was always in our roadmap, but looking back, we all agreed that it probably should have been the first thing that we looked at and looked at really hard. ActiveRecord encryption with the backwards compatibility key list makes key rotation really, really easy, so take advantage of that. All right, what we thought we knew. 1 byte in, 1 byte out. All of our ciphertexts are the same size. Sorry, just double checking that this slide is showing everything I wanted to. So AES GCM 256 works like a stream cipher. Some cryptographers in the audience might be saying, oh, but it also works like a block cipher. This is true, but we really don't have time for that today. I'm happy to talk to you about it later. And all the ciphertext will be 128 bits, right? So that sounds good. Some columns are migrating from plain text, but they just need to be resized to hold about 128 bits, right? I think some of you see where I'm going with this. Our previous encryption scheme stored some metadata, but it didn't store quite as much metadata as Rails does, and not quite in the same way. So what did we learn? Ciphertext is not a one-to-one mapping to encrypted record, or what ActiveRecord encryption Cipher calls the encrypted message. And while we accounted for some overhead and migration to the new scheme, we didn't fully think this through. All of our ciphertexts are the same size. That is true, 1 byte out, 1 byte in, 1 byte out there, yes. However, ciphertext is not all that is stored in the database. Rails embeds a key ID as part of a simple envelope encryption strategy. It stores all of this in an adjacent object, and it includes like a couple of other headers. If you want to add values to this envelope, you need to account for the size any of these metadata bits may be adding to the total size of your record. This one, we thought we were being very clever. I mentioned before we have our anti-nonce exhaustion data. That is quite a bit of text. I think that might be 26 characters long. We wanted to write for readability, right? We were writing this, and our previous encryption scheme was really good, but developers didn't totally get how it worked. So we wanted to just be so explicit and clear with everything, in case they wanted to look at the internals and see the changes that we had made. This is the actual name of the tag that we used. If you are familiar with envelope encryption or the types of metadata headers that get appended to ciphertext in encrypted messages, you know that usually the names of these tags are just 1 or 2 characters. So just for a bit of comparison, you can see our previous strategy. In red, we have a key ID, and then in gray is the encrypted message. And these are both packed as binary strings. So this comes out to about 42 characters, which is quite small, right, and quite nice. ActiveRecord encryption uses a JSON object, which I think is also a nice way to store an encrypted message. And we did consider, that there are headers added differently and a little bit larger because they are an object and not, a packed binary string. But you can see ActiveRecord encryption, the payload with the key P, is quite small. And then the message headers with the key H is a bit bigger. I think this whole thing comes out to about 208 characters, only 60 of which are the payload. And you'll see at the bottom, someone has added a very long message tag with the name anti-nonce exhaustion data. So we ended up resizing our existing columns and recommending that all of our new encrypted columns use the type MySQL text. We made this recommendation based on the fact that we are not allowing deterministic encryption at GitHub. You probably don't want to can't use text if you need to index on your encrypted columns. I personally feel that encrypted records should not be indexed on, and you should not use deterministic encryption. But as happened at RailsConf, and as I'm sure will happen here, someone will tell me a good use case that they have. But for my org, for our use case, we've decided not to enable deterministic encryption. So if you need deterministic encryption, just make sure that you use a large enough size column, but probably not text. So what can you learn from our experience? Really, truly, if you are making any changes to the message headers or the metadata, understand the size of those bits that you're storing along the ciphertext. In our case, we really did not need to name the tag anti-nonce exhaustion data. Product engineers were not quite chomping at the bit to dig into the internal changes that we made and really wanting to understand the API at that level. So we may be over-optimized for thinking people would be as excited about this as we were. Although they are quite excited about what it buys them. Next is the actual value for any header values that you may add, right? Our anti-nonce exhaustion data is the year. We determine with the number of encryptions that we do every year. Rotating the key yearly automatically in this way would be sufficient for us. The most important thing about this value, I think, is that it is of a fixed length, right? So you wouldn't use something like a model and a column name, because those are not fixed length, right? They could be different lengths depending on the model and column. And you might be thinking, Kylie, year is not guaranteed to be fixed length. And that's fair, but we do have about 8,000 years before that value will become longer. And I think that this is probably enough time for us to figure out a solution if we need to make a change. However, because we use text, I think we will be okay if we add one more character. Just to highlight, once again, all of these other message headers, which are implemented by the Rails team, are just 1 or 2 characters, and our message header's name is quite long. So make it easy for your engineers. Don't even let them find out about the size of message headers that will be added to the encrypted message, right? So consider longevity. Like I said, using text and using year for our anti-nonce exhaustion data does buy us about 8,000 years, and we have a lot of work in the backlog, but I think, if it comes to it and we have to make a change, we have the time. That's a joke, so you can't laugh. Or it's your morning too. So what we thought we knew. The price of it just works is performance, right? When something just works, you pay a price, right? And we assumed that this would be performance, right? Encryption can take some time. But we were moving from one encryption scheme to another, so our engineers were familiar and understanding of how much time would conceivably be added, right? And so we figured that this was negligible, and for those upgrading a plaintext column to encrypted, again, it will just be such a small amount of time, and it's acceptable to our engineering team. So what we weren't thinking about was the price of item potency, right? Sometimes you pay in how much time, and sometimes you pay in how many times. If it just works, how did we find out? With monitoring, and unfortunately with our customer audit log, which some of you may have noticed. So we had a bit of a red herring, and we found that some of our custom code was somewhat of the problem. But what we ultimately learned, some data is just extra special. And we had one such extra special column, two-factor recovery codes. We had monitoring in place to measure things like encryption and decryption failures, but we didn't have anything internal in place to measure side effects of our upgrade strategy. Our upgrade strategy relied on a type to feature flag, right? The flag would determine if a record should be encrypted or not, and it would be set to encrypt before we ran our upgrade migration. And this seemed like a good system, and we upgraded a couple columns from our previously encrypted strategy to encrypted, and we saved what we felt was like a special column for a little bit later, making sure we had really battle tested it before we tried this one. But we overlooked that this column relied on changed in place, right? So when we were migrating this column, which was previously encrypted, we found that changed in place would compare decrypted plain text to the encrypted cipher text. And this will always show as changed, right? This is the virtue of encryption. This is the main value of encryption. Knowing the cipher text should tell you absolutely nothing about the value of the plain text. So the encryption works quite well. But we neglected to delegate that changed in place method to the ActiveRecord encrypted type attribute, right? So when we migrated this column related to two-factor authentication, this had the unexpected side effect of causing all of these records to appear to have been changed when they were in fact not. And this generated audit logs for our customers. Fortunately, though, there was no actual change to the data. The data itself is fine. And our authentication team was really great and very understanding, and they annotated the false alerts to indicate this to the affected customers. We fixed this by delegating the changed in place to the encrypted attribute type. And this now compares the decrypted ciphertext to the plain text, which, again, if encryption was done correctly, and with ActiveRecord encryption it is, always match. So we also noticed, and this was the red herring, we thought perhaps our issue is item potency, right? The idea that maybe to get something done, a method has to be called a couple of different times before it can really fully take effect. But the encrypt method is item potent. But we noticed with our monitoring dashboard that encrypt was being called twice. This did not directly contribute to the erroneous audit logs, but because we generated these erroneous audit logs, we did notice this. However, luckily, like I said, encrypt is item potent. There is a 35-second period where I was extremely ill, thinking that we had double encrypted records and thinking, oh my goodness, how are we going to find out which ones are double encrypted and how are we going to decrypt them and set them back to, the standard single encryption strategy that we have? But like I mentioned, encrypt is idempotent, and the bug was fixed if you are, for some reason, like us, relying on counting the number of encryptions or decryptions to detect potential failures. Yes, and the bug has been fixed, so you can rest well knowing that it will only be called once per encryption, which is, I think, a really good and appropriate number of times for it to be called. So what we learned, it just works means, right? It did just work for most cases. But we had a really special case. And monitoring can help detect special cases, but the problem with monitoring is it's too late. This is in production. The special case has hit production and could now be affecting your customers' data. Some data is just extra special, and you need to take extra time and care to get it right. So, what can you learn from our experience? Maybe, don't meddle with the internals, but maybe you, like us, can't help it. Encrypted data is being encrypted for a reason. There might be special monitors or side effects associated with these records. But despite all of this, all of these bad things that seem to have happened, and quite a bit of sweating on my part, we delivered a seamless column encryption strategy. We're no longer maintaining divergent column encryption code. We have this new, easy-to-use process to upgrade columns from plain text to encrypted, which before we could provide, but was difficult and a bit arduous and not appealing to our developers. We greatly sped up development time of new encrypted columns, which greatly increased adoption of encrypted columns. And we maintain our service level with no service interruptions at all. So I think if you keep a couple things in mind, you can too. And the two that I think are most important probably are to build with key rotation and key management in mind first. I mentioned this before. ActiveRecord encryption makes this very, very easy, and you should take advantage of it. You could probably build your own column encryption strategy, right? But building your own key rotation strategy without the support of ActiveRecord encryption is very difficult, and I do not advise you go down that path. And then the next most important thing, I think, is understand why a column should be encrypted and what side effects there may be on those records, right? This is live data. This affects your customers. This is the livelihood of your application. Deploying seamless column encryption was not seamless, but it's very doable, and I really believe that it's worthwhile. If you enjoyed this presentation, if you'd like to learn more, we have 2 blog posts that detailed, first, all the changes that we made and why. And then we have another one that tells you in more detail how a kind of like simplified version of our key rotation strategy, and it has some sample code, which you can use, and it relies on this really handy gem that I like from Shopify called maintenance tasks that helps you handle these kind of like special transitional migrations. The ActiveRecord encryption guide, which I joked earlier, but it really will take you very far. This presentation is just about the handful of things that weren't in there. We gave a presentation earlier this year, which kind of maybe sells you on ActiveRecord encryption a bit if you're not sold. And then 2 of my absolute favorite security engineering books that I've read, Real World Cryptography by David Wong. I opened this book probably like every day or every other day while working on this project. And then I really enjoyed Google's Building Secure and Reliable Systems book. It's kind of their security answer to the SRE book. Yeah, I don't know that we'll have time for questions, but I would love for you to come ask me them in person, or if you feel shy to come, you can message me on the conference Slack. Thank you so much.